Thank you very much. So this is a joint work with Ghani and Pierre Hyvernat, and I'm going to talk about arrays. So here's a small story of creation of arrays. So in the beginning, there was not a word, but a rank 0 array, and life was beautiful. And then somebody had to invent a sequence to make a word, which is also known as rank 1 array. And after that, it wasn't enough. So somebody invented n-dimensional arrays of that type. Well, what is this type exactly? So a lot of people, when they see kind of this problem of n-dimensional arrays, they immediately jump into idea, okay, if we have vector types, we can just, iterate them and take something like a free monad over a vector type, and here's roughly how could it look like if you embed the vec into the data type. You can have a list of natural numbers, which is the shape of your array, so you can extend across all the n axes, and you can have scalars, and then you nest your vectors, and you carry on, you remember how long each axis is, and then you put them into a shape. But this is not really the holy way to do this. The better way to do this, in some sense, is to notice that this free monad is, can be expressed as a representable functor, which is represented by this type P, which in this case is actually quite simple. So we also have a shape, which is a list of natural numbers, still extend of all the x's, but now indices are shapes, are a list of natural numbers that are element-wise less than the corresponding shape structure. And then the big idea is that array is just a function from indices to values. And if you think about it, that's really what arrays are. You just look in the element and you get the value back. Okay. So why this structure, why this representation is sometimes better? I often propose people to write a generalized transpose. So, I mean, from the experience of array languages and array theories, we know that if you want to define combinators on arrays, you'd better do it in rank polymorphic styles. You want to operate on arrays of arbitrary rank. And if we, for example, if we want to define this transpose, which is just you're given an array of shape S, and you need to compute an array of reversed shape. In the functional style, it's just an indexing on a reversed index. And if you go in this free monad style, it is much scarier construction. It's possible, but it's just quite unpleasant to work with. Okay. So, and these arrays are functions, and they are very well-behaved functions. So the structure is kind of homogeneous. So you can define all kinds of combinators and basically start building your array expressions in very kind of high-level rank polymorphic style. So far, so good. And for example, here's a simple example of a rank polymorphic matrix multiplication, kind of generalized, and you can see that the important bit here is that these S, P, and Q, they are not natural numbers, they're just arbitrary shapes. So this is really kind of some kind of tensor contraction thingy, right? With the appropriately chosen operations. Okay, so this is good, and you can keep going. But we do know that there's an entire theory of this approach called containers, where we want to talk about data types represented as functions from indices to values. So just to remind you, because we haven't seen definitions in the container session yet, so a container is a pair of shapes that are sets and positions that are families, and then the interpretation of a container is when you take some shape and the data is a function from indices of that shape into values. Okay. So containers have plenty of properties, and for kind of this talk, it's going to be important that they have some kind of algebra. So we can build new containers out of old containers, defining these operators. So quickly on this slide, we have a container 0 that has no positions. We have container 1 that has exactly 1 position. We can add them together. So we can add positions of 2 containers and put them in a new container. We can also take a product and a tensor product. So difference is what do we do with the positions. Okay, and we have plenty more stuff. Okay, so then containers have a morphism, so it allows us to define a piece of data if we have which we can translate the interpretation of container A into interpretation of container B, and all we need to have is a function from shapes of A into shapes of B, and the functions from the positions of B into positions of A. So this is contravariant. Okay. And yeah, okay, and these guys together, so containers with the morphism, they form a category which is also very well behaved. Again, a lot of people study this question many times. Okay, so now the question that I've been interested for a long time: what is a good representations of these n-dimensional arrays as containers? And here's an answer that we found many years ago with Peter Hancock. It was mainly his idea, but so the idea is that we found a new container operation that we call generalized tensor product that looks like this. I don't have a lot of time to explain all the details, but the intuition here is that we take container CD, the right thing, and we tensor product it with itself as many times as we have positions in the container AB, right? And if you unfold the definitions, then it turns out that the array that I showed you before is just the tensor product of container NatFin, right? So it's kind of a bit magical, but if you carefully unfold the definition, it's really what's happening. So are we done? Well, we learned from Connor on Monday that natural numbers is the source of capitalism, right? And we can't kind of live with this, so we have to do something else. So the idea that we kind of the key slide of this entire talk is that we started to think, okay, what are the other ways to represent these arrays and maybe tensors even nicely? And from array languages, we know that the key to any representation is how rich your shape structure is. So if your shape structure is rich enough, then you can define many very interesting combinators and your life is good. So what is the richest structure we could possibly think? Maybe container itself. So what if we're going to use containers as the shapes of our arrays? Well, how do we do this? So what we need to kind of define some intuition, and the intuition here is this. So if we have a container AI, then A is a set that enumerates the axis of our array, and I is giving the type of index at this axis. That's it. And then, okay, for example, here is an example. So we want to talk about matrices of m by n. Then the shape in container language is going to be container of shape 2, and well, the positions is fin n and fin m. Okay. So, but how do we then get the data of this container? So, array of this container shape. So, for that, we can't use the standard interpretation anymore. We need to define a new interpretation of a container, which you see on the slides. And what we do, we take a container and we product AB, and that's going to be our index space. And from there, we take a function into the values. So why? Because we just defined, so what is this pi AB? It's A many B's that we put in a big tuple, right? So what we have is like a large tuple of the kind of index types that we have defined as in the positions, okay? And so it turns out that this is good enough for many interesting combinators. Okay, then the question from here is goes two ways. So first of all, what kind of combinators we can define, and secondly, okay, what kind of creature we're even dealing with, because here's something going on, and the question that we don't have a very good answer for is the following. So it seems that if we look at the AR itself as a container, then we need to move to these categorified containers, because we are using con as a kind of a shape, right? And then we do something with this con in order to get a family. So in some sense, you can think that AR is an instance of this categorified container where the category is containers and the family is pi that just puts A and B into the pipe. Yeah? What do you do with this information? I don't know. We don't understand it yet, but it seems that the connection is this. Okay. Then it turns out that we can define a bunch of combinators and observe a bunch of properties. For example, we have this very convenient and very useful nest-unnest pair of combinators that kind of demonstrate a kind of monoidal structure. So you can move between the shape S plus P and between the nested array S of array S of arrays of P's and backwards. You can have some kind of, I don't know, Cartesian product or generalized Kronecker product by, if you just, you take each with each. And then, importantly, we have two kinds of maps. So the first map is kind of obvious because you have just a function into X. So obviously you can map something to all the elements by pre-composition. But the other map is interesting. So the other map is very important in the array world because this gives you array reshaping. So what you typically do when you write these programs in higher dimensional arrays, you try to carefully select hyperplanes of the elements that you like and reshuffle them into one side of the array, kind of back or front, and then kind of nest and do some map or reduce. That's typically the game. And so it's very nicely that the original container morphisms act as these reshapes on this interpretation of arrays. Okay. And then finally, so what we observed and what made this entire discussion resulting in some papers. So we observed that we can, first of all, we can define tensor contraction or this generalized matrix multiplication, as I showed you, on this type. So array S plus P, P plus Q, S plus Q. So it's almost like matrix multiplication, but this gives kind of a category of tensors where objects are containers and the morphisms are arrays of S plus P with some fixed field X and the restriction that P has to be finite. And the composition in this category is just this tensor contraction. And yeah, this gives in kind of under this interpretation, what does it mean to have array AR S plus BX? It means that we have S covectors and P contravariant vectors. 0 and 1 are singletons. Actually, 0 and 1 are the same under this interpretation, which is funny. And yeah, we can turn array SX into a column vector or a row vector like by simple manipulation, so like a almost hidden metric tensor or something. Okay, so this is really where we are right now. So we noticed this novel way of interpretation. So we defined a bunch of combinators. We formalized some of this. And yeah, would like to hear your opinions and maybe do something else. So a note from Neil, he's hiring for his new startup, and I'm constantly looking for good PhD students. Thank you very much.